with ball bearings in class number 11. We introduce section 11.6 where we combine radial and thrust loading. Here again we have like an apples to apples mission where we're trying to figure out a way to take our scenario, make it compatible with the catalog. Well, the catalog is only for radial load. So we need to figure out some way to make an equivalent radial load for a given scenario of combined radial and thrust. So if you have radial and thrust loads taking place in your design scenario and you need a bearing that can do that, you want to go through this process. And unfortunately, it's a little bit of an annoyance. So you can see that what you can do you could handle some radial load, some thrust load with a ball bearing, with a regular ball bearing, but especially an angular contact bearing. But if it's with a roller bearing, you need to have like a taper onto the thing to be able to handle an axial load, a thrust load. And I like this from another book right here where they kind of show some of those clearances and they show the offset for that clearance. And by the way, when doing this, sometimes we'll say that this is a preload onto a ball bearing, which is to say that there'll be some type of method of, sometimes like as part of the housing, sort of like a spring to push the inner raceway so that it's got like just a little bit of a firm push onto it so that it will be touching, the surface will not really touching because there's oil in between, but they will be already be set so it won't be rattling around when there isn't a thrust to be had. But that you could also kind of see that's where the thrust is being handled by way of having that diagonal line of force. So here is also a bunch of stuff on one page, and it might be a little overwhelming, but we'll work through what of all these things are. Essentially, this table 11.1 and this figure, let me call out the figure, it's figure 11.6. 11.6 is really a plot of 11.1. And all we're really looking at here is trying to find some equivalent force, this FE. The FE is what we're seeking out, and that's what we will use to go toward and work through the other things that we've just manipulated to get a catalog rating. So that's going to be our new desired load, right? But if we have some axial FA right in here, and we want to take a ratio of the axial and the radial, right? So the ratio of the axial to the radial, and you see a V in here. It's not really very necessary because we most of the time we have a scenario where we have a stationary outer ring and a rolling inner ring, right? So that's the kind of like most of the time what we're dealing with. But if you had the other thing going on, right? If maybe you have a stationary shaft and you have something that's spinning onto it, like, you know, I don't know what it might be. Maybe it was a windmill or something. I don't know. But you have a stationary shaft and you put a bearing onto the thing and it's the outer ring that's rotating while the inner ring is stationary. You use 1.2. But otherwise, just think of it as the ratio of the axial to the radial, right? So if you do that, there's a slope line and you can see a bunch of dots and they indicate that that's from experiment, right? And you'll see where you can find the intersection right there. And then you take the equivalent, you'll find there's a ratio of the equivalent to the radial. Simple. One thing that makes it a little complicated is that you will have to, below a certain limit, this E right here, then the you see the axial doesn't matter. Right, we'll see that the ratio of the equivalent to the radial is equal to 1 right here. So that is the graph right here. Well, that's also done by way of this equation right here and this table. right? So that FE that we were looking for up here is represented right here. And for whatever reason, they decide to make this seem a little bit more complicated than it needs to be. So you have this XI, capital XI, and it's either one, this I is either 1 or 2. That means you're either using this column or you're using that column for the values. And if you could see that you use column 1 if the ratio of axial to radial is less than E. Up here at this figure, you'll see that E is like this boundary. And you can see that this column right here tells you what the E is going to be. And you'll notice that x1 is equal to 1, y1 is equal to 0. Go back up this equation, and all that's telling you is that if you're below E, the equivalent is equal to the radial. Great, golden. Don't have to even worry about it. Axial doesn't matter. That's what it says. The axial is small enough that it won't affect, and just go ahead and just use the radial load and go and monkey around, find the catalog rating, go to the catalog, you're done. If the axial is larger, if the ratio of axial there is larger than E, you need to use this 0.56 and this y. And you can just think of the 0.56, that's the slope of this line right here. And this y, that's really sort of like the intercept of this thing. So not a big deal. The only problem that we have here is what do you decide, what row you decide to use on this table. And that's kind of a pain because you see it's a function of the axial divided by CO. And you go, well, wait a minute, what is CO? We've been doing C10. Well, CO is the basic static load rating, right? So if the thing is not rotating and you just want it to be sitting there non-rotational, then you know, this is like the capacity of the thing. And so it struck me as strange is that it's a smaller number than the C10, right? So so you'll see that we have a CO right here. But now the question goes, well, wait a minute. How are we going to know what row to use if we're trying to find this, eventually get the number C10 so we can pick out the size of the bearing, but now we need to know the size of the bearing in order to pick out the size. I mean, it's a circular argument. Well, that's the annoying part. You have to do an iterative solve. You have to solve iteratively. So, but it'll converge to a solution. It's usually not more than twice do you have to go through it, and it really depends on what you choose as your first value right here. So the procedure is really to start out with just use the radial, right? And go through and find a C10, go to your catalog, base that C10 right here, pick out one, and then find your CO. Now come back into your catalog here, come back into here and take your axial and the CO you just found, and then find, and you have to interpolate, that's an annoying part right here, you have to interpolate in here and find what your E is, right? Double check your FA to FR, are you above or below the E? And that determines which column that you're in. Most of the time, we're going to make I'm going to invent a problem where there is a sufficient axial that you have to go through here. So we come through and we look at, and like let's say that we magically landed on a FA to CO exactly of 0.056. Then we're going to use for X2 and Y2 0.56 and 1.75. So what we're saying here is we take 56% of the FR, but then we multiply our FA by 1.71, and that's our equivalent. So then we use that in conjunction with this equation. We plug it in for right here, except that right here, right? We put that FE into here and find the C10, come back into here, depending on which one we're using right here, find, is that the same gear that we had before? Oh, that same gear doesn't do it. We need a larger capacity gear because now we've increased the amount of the effective or equivalent radial load. So now we have to do it again because maybe we have a larger number, so we have another C0 depending on which one we were using right here. So we have to come back over here and we have to do it again, and we find a FA to CO with this new CO that we have for this new bearing, and we find out what these new ratings are going to be, and it wasn't 0.5. And magically, it would be nice that we wouldn't have to interpolate, but we would get the same numbers, we get the right numbers here, and then we do it again. But you shouldn't have to do it more than twice, really, especially if you pick pretty close to it on the first round. So finding the equivalent radial load requires iteration of this table is the bottom line. So I have on the next page sort of like a summation of a bunch of the things, right? So this is out of, I decided that for section 11.8, I would just describe the process of going through, and I don't even know why I decided to call it section 11.8. Their section 11.8 is an example. That's all that's in really section 11.8. If you take a look right there, they just go through here and then they go through example 11.7, which seems to me they should have made the numbers like coincide right here. So that's just a longish example right in here. I decided to like summarize for everything, and maybe I need to change my notes right here because I want to use the other version of this thing right here. But I put it all in one place. And this is what we're going to talk about in the next class right here. So if you're loading and it isn't always the same, you might need to adjust for that. So that's like section 11.7. So I think what follows is an example, and I have a long enough video here that I will now split it up. So this was 12 minutes long. So if you want an explanation, I'll maybe outside of class, this will be the one that I refer you to.